Okay, welcome. Good morning. This is the first of a series of presentations we're going to have this year in Work Package E, which is about long-term and innovative research for SESAR. We have 18 projects coming to an end, and we're trying to have most of the close-out meetings, which will take place between today and the next 6 months, here. Some of them we will have to have in Brussels. Most of them we'll try to have here, and so if the topic is of interest to you, don't hesitate to join in and give your comments. Try to find out what we do with this work compared to the mainstream work in SESAR. Is there any link we can think of, any continuation we should try to stimulate? Today it's about network management, airline operation centers, and uncertainty. And we have a large presence of the consortiums today. The consortium was led by GMV. Jesus was a project officer. He will not present the technical part, but the other colleagues will do that. So we have several colleagues from GMV. We have Arthur Richards from the University of Bristol, who was doing the mathematical work on the network management algorithm, and he will present that as well. And we have two people from Skysoft who are working on representing the data, and that will be demonstrated as well, I think, in the presentation. The first speaker is David Martinez from GMV. He will be followed by Javier, and then Arthur will show the results from Bristol. So the floor is yours.
Okay. Welcome all, and thanks for your assistance here to the ONBOARD meeting, close-out meeting. And we will make a full description regarding the technical parts of the project, which is the motivation of this project, and which algorithms and systems we have developed in the frame of this. And finally, we will review some results and give the final conclusions of this project. Okay, first, a brief description regarding the project, and that is that one of the difficulties in improving the ATM performances is that the ATM system presents those features associated with a complex system. There are a lot of sources of uncertainty. There are many agents that adapt their behavior to the system state. And finally, the constituents of the system, which are the aircraft, basically, present nonlinear behaviors, nonlinear dynamics in this case. So neither nowadays nor in the SESAR concept of operations, those complex features are addressed in order to exploit the performance improvements that they could do. And basically, the information related to the uncertainty is not used to improve these ATM performances. So the motivation of this project has been to research how to improve the ATFM performances by explicitly incorporating information about uncertainty and focusing the analysis and the development in incorporating information regarding the weather and the unscheduled demand. So, in the frame of this project, two core algorithms have been developed, which are the Network Manager and the Airlines Operations Center, which have been implemented into a platform to be in order to run all these simulations and give the results of this approach. Basically, the development of the project has consisted of developing two main algorithms, which are the AOC, which is in charge of calculating the initial plan, generating trajectories, and processing the demand capacity measures, which are given by the Network Manager. The second algorithm has been the Network Manager, which is responsible of computing the demand capacity balancing solutions, including the uncertainty information that we have mentioned. And finally, the Radar HMI, which is the model that generally provides us a graphical visualization of the results from the Network Manager point of view. The system developed has been three parts, three different models have been implemented into a platform. And the idea behind this architecture is that it allows us to exchange data between the AOC and the network manager through a set of centralized databases, which allows us at the same time to develop independently those two algorithms in terms of code or system environment. And the other aspect and the other benefit of this architecture is that it allows us to do data backups in order to run simulations afterwards without the need to run all the models each and every time. And finally, just as a comment, there is a submodule which is the evaluation scenario tool that it only provides us with data to run the scenarios, basically. Generally speaking, the project outcomes are four. The first one is the progress beyond the state of the art that we have done, especially in terms of modeling the uncertainty for decision making in the ATM field, the characterization of capacity and scale demand uncertainty, which is one of the main motivation of the project, and the application also of robust MPC techniques to solve the problem. The second aspect to highlight is the development of brand new algorithms, which are the network manager basically and the AOC, but also auxiliary algorithms such as the scenario generator. Radar HMI also to visualize the simulations and scenarios, and finally the final outcome of the project has been the validation platform to run simulations and analyze the benefits of the approach of this project. In this section we are going to review the technical aspects of the AOC, the Airlines Operations Center, which is basically in charge of generating the initial rotation plans, optimal trajectories, and calculating the optimal alternative plans to meet with the restrictions that are given by the network manager. But basically the structure of the AOC is shown in the figure, which is composed of 5 modules. The scenario generator, which provides just with data to run the simulation. There is the trajectory calculator that optimizes, which calculates the trajectories to be flown by the aircraft. The cost calculator, which also calculates the cost of flying that trajectories. The IP optimizer, which is the submodule in charge of optimizing the fleet assignment of the aircraft. And finally, the alternatives generator to generate alternatives to the initial plans. And just as a note, the AOC optimizes the problem based on the cost model that considers that strategic and tactic costs. The mathematical model implemented into the AOC is based on the concept that many air traffic management problems in the optimization field are considered to be just as a linear optimization problem. But the difference is that the solution variables must be integral values. So this is what we call an integral problem. And the formulation of this problem is just the formula that you can see here, that it tries to minimize the cost function, basically. The model used is the timeline network, which is based on a series of elements, which are shown, you can see on the figure and are described here, which basically makes use of 2 types of nodes. Nodes which are source nodes, which represent where are the commodities of the aircraft at the initial point, the initial time, and the sink nodes where the commodities where the aircraft have to be at the end of the optimization process. So the nodes basically represent the location and time represent two types of data, location and time. The arcs, which represent this movement between nodes. And finally, the commodities, which are the aircraft, which are routed through the network with every arc. Just as an example of this mathematical model, we show this.
This is a graphical representation of what we are doing with the AOC, which is we have an initial set of possible plans to optimize the operation of the airline, to decide which aircraft flies which flight, and the complete rotation of each aircraft between the airports and the schedule of the airline. So we actually represent all the possible alternatives that is graphical represented here. You have its red node, it's an arrival node. So an aircraft in some red node can connect all the future departure nodes that are represented by green points in this map. Yeah, at some point you can have an aircraft here in this red node that can connect this flight, or this flight, or this flight, or could finish its operation in this airport. So we first represent all the network with these nodes and arcs and evaluate a cost for each arc in this network. So using the integral program solver that we have, we can determine which plan of these possibilities is the optimum. So we actually have this solution in this case, where you can see that there is a defined connection for each aircraft. So you have that the aircraft arriving at this node connect exactly one future flight, and some, for example, this one, we can see that the aircraft at this time could fly this or any of the future plans, but the optimal thing in this case is just wait until the finish of the airline operation at this airport. So this aircraft actually finish the rotation plan at this airport. Yes?
Can I ask a question? Is it something that represents a realistic way of dealing with uncertainty on the day of operation in the airlines?
No. The uncertainty in this project is considered in the network manager part, with the weather and unscheduled demand. We are not considering any uncertainty here. We are just evaluating all the possible costs in realistic scenarios to have the optimal decision of the airline operation based on costs related with maintenance, crew, and also considering delays, passenger compensations, fuel, of course.
But is this model developed with airlines, or is it?
This model in this project is about to interact with the network manager to have a realistic platform in order to analyze the core of the research, which is the network manager dealing with the uncertainty.
Because this type of solution might be representing how they do their aircraft planning, their aircraft routing at the planning phase, but when there is uncertainty of the day, it's probably the constraints are different.
Yeah,
they may have
we are going to talk about this later, but the platform that we have designed, it's about to iterate, so we generate a first initial plan, which is the initial ideal operation for the airline. We share this plan with the network manager. The network manager gives us back constraints regarding the network planning with the uncertainty, and then the AOC evaluates a set of alternatives that include delays on ground and modifying speeds in trajectories in order to fly faster or slower. And then we iterate with the network manager with a new solution until the problem converts, and then we have the best possible solution for the AOC, meeting the restrictions that the network manager gives us.
So, considering the mathematical model and all the functionalities that we have mentioned, all this information have been implemented into an AOC prototype successfully. which has been used to just to interact with the network manager and run all the simulations and the integration tests in the evaluation platform that we will talk about a little bit later. So just as an example of the information that the optimizing process in the AOC gives us, this is just a report of the optimization process, which tries to minimize the cost function and while processing all the information related to the flight plans. Talking about the AOC results, the first set of tests that we ran were based on an initial test case, which consisted of a set of 30 flights distributed between 6 AM and 4 PM, and a network of 5 airports with a 5 aircraft capacity limit for the airspace sectors. The capacity reduction scenarios that we consider in this process to generate some kind of uncertainty is based on a combination of 4 separate storms. And the iterative process works as follows, which is that the AOC shares with the network manager an ideal plan scheduled for flights. The network manager applies the restrictions that considering the uncertainty in the process, and the AOC readapts the plans considering that restrictions that are given. And the iterative process just continues, keeps going until all the capacity restrictions are met. Considering the weightings that we gave to the generation of alternatives, we see that there is a heavy penalization of regarding the ground delays. Not all suggested delays are mid-air, are just to fly slow, basically. And the delays are applied to specific trajectory sectors, just as a note. And regarding the alternative plan results, they show that the cost of the solution that alternatives are cost optimal solution of the NM delays, and that are generated both types of alternatives, delaying departure and replanning slower trajectories.
Basically, here we have we share the 30 flight plan with the network manager, and the network manager gives us seven delays for these flights in these sectors, and these are the specific minutes delay. So we evaluate these restrictions back in the AOC algorithm, and we come with a new plan that includes these seven flight alternatives that meet the network manager restrictions. Here in this sample problem we are using on-ground delays and modifying trajectories in order to departure at time but flying slower to meet the restriction in some specific air sector.
Okay, so once we run the initial test, we run a rather larger problem which consisted of 200 flights, 21 airspace sectors over the London area, and 16 airports. So we allowed that both types of the types of alternatives that could be generated were on-ground and airport plus on-ground alternatives. So two kinds of solutions were got, and the evaluation of the performance was done through by means of a set of KPIs, which are basically the direct operation cost, the disruption recovery costs, on-time performance, the percentage of affected flights, and the fuel consumption that we got from the results, which is basically the setup. Here we can see that the results show effective saving of 2.3% in the disruption recovery costs, and that only 3% of flights were affected. So there is a considerable saving in that regard. And finally, the fuel consumption, you can see that in both types of solutions, the fuel consumption is reduced when considering also the airborne alternatives. But this is not. This is just an effect of the optimization process, because the objective function that we are trying to minimize is the cost function of the fuel function. So this is just a secondary effect that we got from the results.
Yeah, well, these are just the results focus on the AOC part. So yeah. We're going to talk later on the results of the network manager and that. But we have compared here two solutions using only on-ground alternatives, which is meeting all the restrictions from the network manager as the restrictions are, use delay in flights on ground. And then we evaluate the possibility of assuming some delays on ground, but also modifying some trajectories in order to departure, to avoid compensation costs for passengers and things like that. And we have some savings in terms of cost from the airline's point of view. These values vary very much between different problems, because we have here only 3% of flights affected, but if you have more flights, or depending on the type of the restriction, you can have different results. But there are generally saving solutions. Well, as David said, the fuel consumption here is reduced, but we are not only considering fuel cost. So it could be that the solution includes some solution burning more fuel, but that it's cheaper for the airline in order to all the costs that have been considered. Yeah. So,
crew change. Hi everyone, my name is Arthur Richards from the University of Bristol. Within the ONBOARD consortium, we've been responsible for developing the network manager, which I'll tell you a bit more about now. So, what does network manager do? Loosely speaking, it does tactical flow management operation. So, some of the horizons are probably not quite consistent with what's properly tactical and so on, but we've been more focusing on the formulations than actually on sort of scaling and exactly where you'd apply it. So bear with me with some of the misuse of language. We're using an aggregated network flow model, which I'll say a bit more about in a moment. It uses the same integer programming optimizer as the AOC was. And the key contribution to this, now there's been a lot of work in these aggregate flow modelings and things like this, and there's a lot of papers available about different ways of doing it. The big contribution that we've made in this project is the ability to include uncertainty in that. So the question is, how are we including uncertainty? Well, one thing you can do, so we are planning some way into the future. Of course, we're going to replan when we get there, but if our plan ignores uncertainty, that limits how good it can be. So one thing we could do is just simply ignore it, or plan for the most likely set of outcomes, and we plan for one scenario and one set of decisions, and that we're calling nominal, and that's problematic, of course, because it's, there are a whole lot of other things that may cause that just to break. You could do robust planning, where you try, and by that we mean you could try and come up with one plan that would work in every set of outcomes. And that, of course, is hugely conservative, because there may be an outcome where one airport is shut, there may be another outcome where another airport is shut. So the only robust outcome is not to send anyone to either of those two destinations. That's obviously massively conservative. So instead, what we've done is put in what we call feedback in the planning. So the point is that as you're doing the plan now, so what is it? It's 11 o'clock. I'm planning for the next 2 hours. My plan will include changes in the things that I could do, different options for the things that I'm going to do at 12:30, depending on what information becomes available at 12 o'clock. And that feedback from the stuff that I'll find out at 12 o'clock to the decisions I'll make at 12:30, we actually model in the optimization. So this is what we mean about feedback planning. A little bit of background about the model. Again, many of you may be familiar with this because there's a lot of research on this. So this is this idea that rather than modeling the motion of individual aircraft, we lump everyone together into an individual, into a network flow model. So we don't model each aircraft XYZ. What we do is we model how many aircraft are there in a given cell along a given route at a particular time. And then the decisions we make are things like how many aircraft are we holding back in that cell and how many aircraft are we allowing from one cell to the next at any given time. So that's why it's called aggregated. Of course, what you have to do then later on is disaggregate, and you have to then say, well, actually, if I delayed 3 aircraft in that cell at that time, which 3 of the aircraft that were there were there? And that's a step that you do at the end. But that's a different topic, if you like. These things have been looked at for a long time, and things that have been fixed with them. We've adopted a lot of stuff to fix the issues with this. So one thing you do is you have a separate network for each destination. Otherwise, aggregation models give you the lovely feature that you'll get the right number of aircraft arriving, but they won't necessarily be the right ones. That's obviously not particularly desirable, so we end up with, as a simple way around that, you just have a different network running in parallel for every destination. You can put rerouting in, so I've shown this example here where we have our little cell model, and actually you can have different routes, but we haven't done the routing in here because the way the onboard project is looking is that the routing is the responsibility of the AOC, so that's not covered in here. The other thing that we've done in here is that you keep, one of the problems with these is that you get what's called a dispersion problem. So people have said, well, you know, you've got a certain number of aircraft in, say, this cell, and then you can say, well, 0.7 times that number is going to be in the next cell at a given time, and they split things. And you end up with these very weird effects where you end up with sort of 0.1 of an aircraft in a cell at a given time, and things get ugly that way. So this forces us to use integer optimization, the same method as the AOC was using, to solve this problem. So, the big thing we're going to do then are represented as integer variables. We're deciding how many aircraft are you going to hold back in cell I at time k, and how many aircraft are you going to move from I to j in time period k. And then you compose this as a cost function, so for all the people who are, for any cell that's an airborne cell, you can count the UIs, and those are the air delays, and then you can count the ground delays similar for everyone, and you can weight the delays separately. So it's very simple from this model to extract what the different delay costs are. And then the big thing we're trying to satisfy, of course, are our capacity constraints. So we have a capacity of each cell at a given time, and then we can add up, so this is the number of aircraft in a cell at a given time that you can wash back through the model that we had a moment ago. So, the big question is then, how do we put uncertainty in? Because what I showed you a minute ago, where we had that constant capacity for each cell, what we're interested in, of course, is the fact that that capacity may be affected by other things. And there's 2 things we're looking at. One is unscheduled demand, and the other is weather. We have 2 ways of doing this. Why do we have 2 ways of doing this? I'll tell you in a moment. But bear with me, and I'll describe each of the methods individually. So the first one is to have what we call a scenario tree. So for example, here we have a picture of, here's the area that we're working in, here's a storm that comes down over Northern Ireland, hovers over London, and then moves on over mainland Europe and heads off in a strange direction. We haven't looked very carefully at sort of detailed weather modelling here. It seems perhaps a rather odd thing for a storm to do, but that's what we're modelling. And there are different scenarios that it can take. So for example, it could come down here, and then it could stay there for a while, or it could immediately move on. And every time, if you like, the storm changes its behaviour between different scenarios, we have one of these, what we call a break in our scenario tree. So this is the state of the world. Time is moving from left to right, and at each one of these breakpoints, something can go one way or the other. So, and we model those as these W variables, where you can split between one variable and another. So maybe this means that, oh, well, is the storm going to stay over London for an extra hour, or is it going to immediately move on? That way it stays, that way it moves on. And then depending on what happens here, or maybe it moves on even quicker, or maybe it stays at its next place and then moves on. So we have these 4 different scenarios, but they're modelled by these 3 different binary variables. And for each one of these variables, or for each one of these scenarios, there is a sequence of capacities. So if you went down this route, then we know how the capacity changed at each time. And so we model this with this weird thing Q here that modifies the capacity limit. So we can put that into our constraint. But of course the problem we have now is that now our constraint depends on this E thing. E is the scenario in here. Don't ask me how we came up with the numbers, but we ran out of letters at some point. So there's E. And of course we have to make sure that this is going to work for all of our E's. And the other thing that changes is the demand. So I haven't mentioned this F term, but F turns up somewhere in the calculation of U, or in the calculation of the thing that drives U, and F is the forcing term on the network. It's the number of aircraft that are introduced. And so of course if you're modelling unscheduled demand, then your F term varies with E, the scenario, as well. So this is the point, is that we have these different scenarios, and what we'll then do, if we jump to the next slide, is rather than simply having one decision, UI at time k, UI is going to be now set equal to a fixed decision plus a feedback term m multiplying the previous scenario variables. So the point is that depending on this could be what I'm going to do in cell X at 12:30, and that's going to change based on the W's that will be observable at 12 o'clock. So at 12 o'clock I can tell whether or not the fog over London's burnt off or not, so that means I can basically model that as a W that's observable. And then this M is a decision variable. So this is a new decision variable in my optimization. So now what I'm calculating, what I'm optimizing is not just a single set of things to do, but I'm optimizing a policy of things that I could do over the course of the period that I'm planning for. Of course, the big problem with this is computation. And this is one of the reasons we're working on this, is because if I try and plan for all eventualities, you can think in your head this is a bit like playing a chess game. What I'm doing now is not just planning a set of moves, but I'm planning a set of moves and counter moves in response to every possible counter move over a sequence in ahead. So you can imagine that this is like a tree that grows and grows. You can see there's going to be an exponential growth in sort of size or number of scenarios. And so the big challenge here is how do you manage the computational complexity of the number of decisions you're now planning for. One of the ways, it turns out that this feedback model is actually quite a neat way of doing it, because you don't need as many W's as you need scenarios. You don't need so in the previous one I had 3 W's, but I had 4 scenarios. And so therefore I don't need as many, I don't need to make a separate set of decisions for every possible outcome of the world. So this is one way of solving this one. And then what we can do is just pose this into the objective in very much the same way. So so basically we go through and we replace all these U's with this thing everywhere throughout our model, and on we go. A second way of doing it. A second way of doing it is to think of these things as virtual aircraft. So remember before we had UIs that were the number of aircraft that we were keeping back, or the number of aircraft that we were moving. We now introduce U tildes. So this is a different way from the W's. We'd introduce these U tildes, and what we're doing is modelling a whole set of aircraft which are beyond our control. And these we call the virtual aircraft. We used to call them the phantom aircraft, but we decided it was a bit dramatic. The virtual aircraft, and the point is that these don't really exist, but they turn up and they rob you of your capacity. Now they could be that they're real aircraft that turn up and get introduced into points of your model unexpectedly, and that's unscheduled demand, because you then take control of those aircraft and you get to do with them. Or it could be that they just run around in a parallel network completely beyond your control, and that represents weather. So if I say there's 3 virtual aircraft in that sector, then that's 3 slots that I can't use because I've had to reduce the capacity of that sector due to a weather issue. So this is, we can model the whole thing by simply having a parallel version of the same model we have already, but now those things are beyond our control. So what we then do is we take these utility variables which are beyond our control, and of course for each scenario in how the world can play out, there'll be a different set of utilities. So what we can then do is do feedback on the utilities. So now we have a different set of feedback variables, L tildes, N tilde, and they multiply by the utilities, and this now replaces our set of decisions. So it's another way of doing this feedback replanning. Now, why bother with 2 methods? It makes the presentation longer and it makes the whole thing more confusing. Well, it turns out that each one is good for a different set, for a different scenario. Because the scenario version, the version with the W's, is much more efficient if you've got highly independent sources of uncertainty. It's not quite true. The independence argument is a little tricky to make, but weather, for example, if your storm is here, it cannot instantaneously jump to over there. It's got to go there first. So you don't have a complete independence between the different things and the different ways that the world can play out. If you have unscheduled demand, you may have somebody who's going to turn up unexpectedly at Manchester, and you may have somebody who's going to turn up unexpectedly at Madrid. There's very little correlation between those 2 events. And if there's no correlation between them, then it turns out that the virtual aircraft model, you can exploit some things in the matrix structure of how these play out, and you can get a very neat shrinkage of the problem size in this way. And it turns out that you lose a lot of this. Again, what you don't want to do is plan for 2 to the n scenarios, where n are the number of things that can change, because that's huge. So both of these methods will shrink that very nicely, but they work better in different scenarios. So, let me show you some example results. We're looking at an area, so this is an initial set of areas that's just hovering over here. Where are we? So that's Amsterdam. Is that Amsterdam? My geography's awful. Anyway, it's an area that we drew off, and we got some realistic sectors and drew some cells around. So just for initial test case of 30 flights, 5 airports, and looking at a 10-hour period. So we've sifted out the world quite a lot, but we model 4 different storms coming through this, and one of them is subject to speed uncertainty. So it may move through the area and out again very quickly, or it may go somewhere, hover in a sector, and then move on again. So this is where we get the uncertainty that we're planning for. So, what was it? Normally each sector's only got a 5, so we've really artificially stepped on the capacity for this to make this work. So normally each sector we're saying has only got a 5 aircraft capacity, but if you've got a storm in that sector, then you can only have 1 in there. And then we break the world down into 5-minute time windows and see how things work out. So, next slide shows the results. And again, we're planning these 4 different, we've got these 4 different sets of results that we can look at. So, here's the initial plan that we got from the AOC. So this is what the AOC really wants to do. If we then evaluate how well that will work in each of our 4 scenarios, so this is the different ways that the storm could move. Of course, there's no delay in any of them, because that's what the AOC wants. But depending on how bad the weather is, we get a significant number of breaches in capacity in terms of the number of time periods in which we are over capacity in a sector somewhere. What we then do is run the network manager, but looking only at the nominal case. So in this case, that's C1, and we say, right, come up with a set of delays that will make the nominal case work. Now you can see that when we then evaluate that for all the possible scenarios, now it turns out that that works for the first 3. Because we put enough delay on that there's not enough pressure on the system anymore. We can see it's doing the same amount of delay in all cases, because it's only really planning for 1. So of course it doesn't know that the world isn't the way it planned for. But then we still have this problem. In the 4th scenario, we went over capacity in a couple of sectors. So just planning for the nominal has helped, but it hasn't fixed the problem, obviously. We can then go robust. So this is where we're trying to find a set of delays that will work for all possible scenarios. So again, we're applying the same delay regardless, because we're still only coming up with 1 set of delays. So we've got higher delay now because we're more conservative, but now we don't have any capacity breaches. So this is the extreme of being conservative. We're delaying everyone to make sure that whatever happens, we don't go over capacity. Finally, we have this one here, which is the disturbance feedback, and this actually used the scenario model that I showed you a moment ago. And in this case, what you can see here, and this is the interesting thing, is that the amount of delay applied is different depending on which scenario. Because, of course, the scenario feeds back from what it actually observes the weather. Sorry, the decisions feed back from what goes on in the weather. But nevertheless, we have no capacity breaches in any scenario. So this is the big deal of the feedback, is that we can achieve this, no capacity breaches, but without having to be as bad as this, and without having to be conservative. And this looks relatively forgiving in this case, but again, if you think the experience tells us that in other applications, the idea of doing robust planning very quickly drives you to the point where there is no solution. There's nothing you can do that will work in all the eventualities. So this makes this look reasonably forgiving, because it doesn't look too bad here. But hopefully you can see that this has enormous potential to be less conservative, and we can see the beginnings of that here. So over here you can see that these are actually the 2 different plans. So these are taken at the same time instant and just plotting, and we can see that some of the aircraft are in different places. It's really hard to visualize what's going on in this. We'll see more in this in the HMI stuff later on. But hopefully you'll agree with me that basically it's just doing a different thing depending on what happens. Okay, if we jump to a bigger example, we've now gone up to 205 flights. We went over, sort of looked over London where things got busy. Again, it's still somewhat sifted down, because we had to chop out certain flights just because it was kind of, lots of things go straight over, so it's kind of difficult to get data and figure out what they're doing. But we're doing 21 sectors around London, and we're now doing 9 different weather scenarios. I haven't got a vast amount to say in terms of interpreting these results, but the same pattern occurs. AOC ideal is brilliant but violates the capacities. Nominal delays some people but doesn't work for every case. Robust delays everybody massively, works every time. Feedback still works every time but doesn't delay everyone massively unless you need to. So we're seeing the same pattern. The other thing that I forgot to mention on the previous slide, but I'll do it here, is of course there is a cost for doing this. This wonderful feedback method is still more complicated in terms of complexity. So the nominal, you're just planning for one, takes 9.3 seconds to solve. The robust takes a minute because it's got a lot more constraints. The feedback has a lot more constraints and it has a lot more decisions to make. So therefore that's starting to take 5 minutes on the order there. It's not the world's greatest computer that we're doing it on, there's plenty you can do about that. But obviously this feedback stuff doesn't come without cost. Okay, if we move on to a quick example of unscheduled demand. I haven't got any pictures to this, but just to show that we can handle it. And this was interesting because this allows us to compare the different models, because as I said, they work differently for different cases. In the two examples I've shown you before, the scenario tree method always turned out to be the better one. Now we're doing unscheduled demand, so there's 4 or 5 uncertain entry times within a 50 flight problem. So if you then look at the scenarios, you've got either 2 to the 4 or 2 to the 5 possible scenarios. If we look at the number, if we look at the 16 scenario case, so 4 uncertain demand cases, the scenario tree method took 293 seconds to solve and the virtual aircraft method took 173. There's a slight difference because they make slightly different assumptions in the kinds of feedback they can do. But you can see that there was a massive reduction in the number of variables in the virtual aircraft method. So now we can start to see why it's worth carrying these two methods around, because for the unscheduled demand, you're much better doing the virtual aircraft approach. Certainly if we then took the 32 scenario one, so we've got 5 uncertain arrival times, we're getting a massive improvement in terms of solve time, and this is bordering on the impractical even if we did work on it. But they're still working broadly the same. So that illustrates comparison of the two. The big deal in this is to do a lot of thinking ahead of time. The optimizer is often quite good at spotting how to reduce its effort. It won't bother making decisions that don't matter. But it's still not as good at that as we are, because to the optimizer, it's just a set of numbers. Whereas to us, before we put it in, we know that it's an aircraft problem with things going here, and so we can apply extra stuff like, well, there's no way anyone's going to get from here to here in that time. So we can go through and cut out unnecessary decisions. And that's key to being able to get these things to work in anything like a reasonable time. Quick last set of comparisons then. What we've done is compared the robust, the feedback, and the nominal performance. So here, if we're just looking at capacity violations, so of course both the robust and the feedback. So every dot on here is a different test case. And then these blue lines, they just display whether things are equal. So all the axes are the same. And so what we're able to say up here, and this is how many capacity breaks did the nominal, so how many times and by how many aircraft did the nominal solution go over capacity in a given problem, and we plot that against the same for the robust and the feedback. They're combined because they both got the same answer. Of course, the robust and the feedback never break capacity, so they go here, whereas the nominal is quite often going significantly over capacity, and that's sort of an averaged measure. So this shows us, this basically, if a dot up here shows that feedback and robustness is doing better, a dot down here shows that nominal is doing better. And in this case, the feedback's doing better in every case. If we then look at the delays, so this is the robust, the average measure of delay in the robust case, and this is the average measure of delay in the feedback case. So we want delay to be small, so dots up here mean that there's less delay with feedback for a given problem than there are with the robust case for a given problem. And dots down here would mean that the robust case is less delay than the feedback case. So all of our dots are up here. And this makes sense because, of course, the robust method is very conservative. So it's giving you more delays than you need, whereas the feedback doesn't give you any more than you need. This is looking at feedback delay versus average delay. Sorry, average delay for the nominal case. And again, dots down here mean that feedback is doing worse than nominal. But then, of course, nominal goes over capacity. So nominal is just picking for one case, whereas the feedback is going in and adding extra delays in to try and satisfy your capacity constraints. So this is matching the pattern that we'd expect. Finally, we look at computation time. So a dot down here in this case means that the feedback is taking longer than the robust solution, whereas a dot up here, there's one case where the robust solution takes longer than the feedback solution for the same problem. So this kind of goes with what we were saying, is that this feedback does cost you in terms of computation. If you compare it to the nominal, where of course the nominal is just looking at one set of decisions. So again, you've got a very big clustering down here where the feedback is taking a lot longer. couple of things about papers, yeah, I'll leave that in.
Well, just to finish, we can talk a bit about what we had to develop in order to make this work. We have developed several additional tools, like a platform control module in order to control the iterations between its model and the synchronization over the scenarios. We have developed a evaluating a scenario tool that is a little simple tool to allow us to generate some realistic scenarios in order to perform the simulations, not just picking random flights, something like that. So with this tool we can define things like the airport we want to consider, the number of flights, the peak hours in each airport, and the percentage of traffic that each airport is taking in order to model some realistic networks. Then we have here the core of the iteration with all the database and different process that we have talked about. Finally, we have developed well, with the help of SkySoft, we have developed a radar interface in order to perform the view that the eventual network manager would have in order to follow the simulation state. This is the radar interface, how it looks like, and it represents, well, we can see here the geographic maps, the air sectors that we are considering, and then we have the capacity level, which is the actual capacity that we have in each sector from the nominal capacity. So we, for example, we have a storm here that is actually reducing the capacity in those sectors. We have the capacity load, which is with the current actual capacity that the sector has. We evaluate how many aircraft we have in there, so you have the capacity load. Then we can represent information about delays, about regulation in airports and air sectors, and of course we can represent flights, and we can also represent the regulation, the delays, and all the flight information associated with each aircraft. Well, we have tested the current version of the platform in order to see how far we can get with this, with the actual version. So, well, as Arthur said, when you increase the complexity of the problem, you go over too much solver time. So we identified that each scenario, each airport you add, it can be reduced to a number of variables that we have identified as a limit at 100,000 of variables. So we can have solutions here. Of course, if the number of variables is small, you can solve the problem quickly, and then if you go to very complex problems, you need much time. So using the simple platform, which is iterating the AOC and network manager over a fixed set of flights, like 200 flights or 300 flights. These are a summary of the results we have. Of course, as the number of variables is a combination of each parameter, if you increase the flights, you need to reduce the number of scenarios and the number of sectors to make it quicker or possible. And of course, if you have less flights, you can add more uncertainty complexity. We have been considering another approach in order to extend this to a more operational approach, which is the rolling window concept. That actually it's this AOC plus network manager simple iteration. We try to do successive iterations over different set of flights that are varying with time. So at the current time, the AOC and network manager are here, and they are planning for this time. In this time, we consider only the flights that have no departure already, and these two windows are going forward with time. So with this approach, we could cover bigger scenarios in a day of operations. So extrapolating this concept to the results that we actually have for the current version, which is the simple iteration AOC plus Network Manager, we could pick some approximation of how far we can go with this. And depending, of course, of the hours you consider to plan and the capacity scenarios, and of course the flights you are considering in each rolling window, you can deal with this quantity of flights over a day. So in the steering class, with 5 uncertainty scenarios considered and 350 flights each step, you can reach approximately 3,000 flights a day. Well, it's need to be remarked that we are using conventional computers and we are using software language and software tools in order to make research. So we are using high-level languages like MATLAB or MPL, and we are using conventional PCs that are not too much powerful in order to prove and research the concepts. But in the future, the industrialization of the prototypes could lead to deal with bigger problems, because we don't have here a problem of concept or a problem of model. We only have a problem of computational power to make this bigger and consider realistic scenarios in terms of number of flights and number of uncertainty scenarios. In the conclusions, the system were implemented successfully. The AOC approach shows benefits from the airline point of view in terms of cost. The disturb feedback approach implemented in the Network Manager present important benefits, as Arthur presented. The current platform has limits, and these limits are appropriate to study some problems and to make some conclusions in the research field. And this could be extended if some work is done about industrializing the modules, the algorithms, in order to use only low-level software languages and more powerful computers. And well, to implement the complete rolling window platform, further work will be required. And I think this is all. Thank you for your attention. If you have some questions.
It's time for questions.
One question I noticed was in the weighting of the network manager, it penalised holding on the ground more than in the air. Is that right?
This is a configurable parameter. We have tested different approaches, but sometimes when you prioritize to delay on ground, the airlines has less possibilities to optimize the problem, because you are actually restricting to delay on ground. So if you say, okay, you just go later in this air sector at some point, the airline could deal with the on-ground delays and could slow the trajectory in order to meet that restriction that is less restrictive than just saying, okay, departure 10 minutes later. So if the network manager gives only on-ground solutions, the airline cannot meet the restriction without delaying the flights. And this is because we have these configurable parameters. But in some of the results presented, we have prioritized airborne delay over on-ground delay also.
Just a question about the data I got quite confused as to, you did exercises with reduced amounts of data and so on. Are you using realistic data from Prism, or where's it coming from, A? And B, how close did you get to a realistic amount of data compared with what you would expect in your airspace?
Yeah, we don't have real data from any trustable source. So we have developed a tool in order to model realistic schedule and networks. We can configure things like the percentage of traffic in some airports, so you can some kind of model and hub and spoke network or something like that, you can define peak hours in order to concentrate some flights in some airports. And you can have some realistic problem, but this is not real data.
But, okay, so, well, you could have used real data. I think we could have provided some data. The second thing is, how close numerically were you to realistic numbers for the airports, for the airspace, numbers of flights and so on?
First thing, we asked for real data, but it seems to be kind of problematic to have it, and well, we are not comparing the scenarios that we are generating with some real reference.
Just one thing, the data that we are using are taken from ICE database, which is real airports and real sectors, and therefore the modeling of the aircraft we are using BADA model, so the trajectories are quite realistic. Okay, so okay. In principle, it's very similar to real data.
Okay, but I still didn't get numerically how close are you to something realistic?
I think, I mean, we did put up some of the numbers that we were using, right? And it was sort of 5 aircraft
kind of numbers
which
in the air,
were
so
pretty much taken out.
I
mean, that's as close as we've got.
And how close is that?
Well, was it 5 aircraft in a sector at any given time was our average. So I would guess that we're quite a long way below it. I think if you were going to realistically push up, the right thing to do would be to go to receding horizon, but that introduces a lot of other housekeeping issues that we've just run out of time to deal with. So.
I have a question with regards to what you said here. I mean, your approach is a typical linear programming approach out of operations research, and these approaches are known that they earlier or later run into computational problems. You say you can solve that by having more computation power, is something what I was taught, said as well 20 years ago, and it seems operations research and linear and nonlinear programming are still in the same state. And to come back to my question, the motivation you said in the beginning is, I think, one of the motivations is to provide cost optimization for the airline operators and as well network management. Did you try to quantify the additional cost for the computation power you would need? Because if you look to your tables, in the easy samples of the nominational calculations, you have a cost of, I don't know, 3 seconds or 9 seconds. And then if you look further on for your optimal approach, the what is called disturbed feedback mechanism and things like that, you have computation times of 360 seconds compared to 9 seconds in a classical approach. So are you sure you can provide with this approach a cost benefit?
A couple of questions. So in terms of the computation, quantifying the cost of the computation, that's not something we've looked into. I mean, we put up the times, how you convert those into actual amounts and what it would cost to achieve in terms of the investment in computation is not something we've looked at. I agree with you that it's a very glib statement to say, oh, well, we'll use a better computer, but I skipped over a lot of stuff there. There's an awful lot of other stuff that's been done separately from work on disturbance feedback about making these things work quicker. So there's a lot of things work on distributing the computation. For example, there's nothing that says that you have to do it centralized. Now, you can introduce approximations and other things like this at the boundaries, but and there's also work on decomposition methods. So the speed up I was talking about was more related to the algorithmic stuff, which is definitely out there, which exists that you can exploit. I agree that you're never going to get it to be microsecond. It's not going to be something that you're going to run on a microcontroller in a millisecond. It's not that kind of computation. But the speed ups that I was alluding to are algorithmic, not just by a bigger computer.
What is triggering all these questions was the understanding that with regards to the planning and execution of the planning phase and then of the traffic, you're very close to the execution where you would like to position a potential product. And then I think you spoke about data sample data being provided at 11:30 for the flight being executed at 12 o'clock. So we're talking really about the operation, the day of operation, and 30 minutes in front of the execution. So the point is, if you calculate these examples, you must be very quick. You must be in a few minutes, and so you run there in some problem, I think, to get your optimum results in the time that would be needed, that you can still implement that result.
That depends a lot of how many flights or time are you considering to planning in each step. So I think it could be a balance between the power, the computational power you need, and the flights you are considering planning in each step. Because if you are going to plan each 30 minutes, I think maybe it's not the most efficient way to consider the next week for the plan. Maybe just some hours from following these 30 minutes in order to consider these things that are happening now with the weather or with a schedule.
Okay, I have another question.
Okay. You mentioned fuel reduction and you started to provide an explanation. Can you develop a little bit more on that in terms of what benefit, what mechanism has led to that? So can you develop more?
Yeah, well, the fuel consumption is also reducing this in this specific product because this way the airline save money, but it's not a need. I mean, the cost that we are considering involve several costs. So the optimization problem is actually reducing the global cost for the airline.
That I do understand.
Yeah.
Fuel is just part of the global cost.
You have to consider the maintenance crew, the fuel, the delays and compensations, and you can have a solution that's flying faster, burning more fuel. You spend more fuel, but at the end you arrive earlier and you have to pay less compensation, and that could be the optimal solution for the airline. You actually are burning more fuel, but it's cheaper for you, for the airline in this case. So this is just an example, and in this particular example, the airline saved costs flying slowly because the network manager at some point gives some delay in the air sector, and in order to arrive later in that sector, you can departure on time and fly slower. So you save some fuel, but just because of the circumstances, it's not a need. It's not an objective itself. The objective is to reduce the overall cost of operation.
I think it's an unfortunate example. Either it's an unfortunate example because you have a total amount of 470 tons of fuel, and you have a saving, if I understand correctly, of 4 kilos. So I think you shouldn't talk about the fuel benefit you have there. Either I misunderstand.
Yeah, the actual benefit here is the saving in the recovery cost.
Exactly, but then I would take the fuel consumption topic out because it's
from Iliana and then yeah.
So actually you said that you have two types, mainly two types of uncertainties, and so you have two types of models. One is for weather uncertainties and the other was for unscheduled flights. And have you considered the case when you have both uncertainties in one scenario?
Sorry, something I didn't make clear. Both models will handle both types of uncertainty. But our results show that one of them works better for one kind and the other one works. So we can handle both at the same time. You would need to. An interesting question is whether or not you can use both models in the same optimization. Which I think it's probably possible, but we haven't looked at it.
Because this is a kind of hybrid system, so you switch from one model to another model.
Yeah.
And another question, you said you are using mixed integer linear programming. What kind of solver are you using for this?
We're using the CPLEX branch and bound solver.
Yeah, because you have also Mose, which is appropriate for this.
Yeah.
If you can.
We fooled around. We're not using state-of-the-art computers. We are using state-of-the-art software on them. It's a little strange, but you use what you've got, right? So, but I think again to return to the earlier point, since I have a moment, because I didn't quite finish answering your question. You asked me, was I sure if these savings would be delivered? It's a really interesting question because, of course, a lot of hangs on this, right? There are enormous goings on in the algorithmic and the computing side improving this to do with parallel algorithms and distributed algorithms and so on. So I can't be sure, but based on what I see going on in the operations research stuff, I am confident that a substantial speed up is possible compared to what we've shown you. Again, it's never going to be fast, but I don't think we're talking about anything. I think you could achieve what you were asking, which was, can you get it within the order of minutes rather than half an hour? That need not be prohibitive in terms of the computer you need to do it. We're not talking, you know, basements full of crays or anything like that.
Okay, I have two more questions. You first.
So about the AOC model, basically it's like you had one airline having all the traffic, all the flights, and managing them to reduce the overall cost by itself. What would be more realistic probably would be to have multiple AOCs, and then the optimized solution might be pretty different. It's just a remark, just in case you're able to have multiple AOCs.
Well, we use mainly to one model.
Yeah, no, that's understood. It's a research.
But yeah, the realistic way of approaching this would be having several AOCs, giving the solutions to the network managers, calculating one only solution, and then each AOC replanning its operation to optimize individual costs.
Okay, Nadia?
Yeah, actually it was try to recap a little bit what you are trying to learn through that. Can we make a conclusion from these initial results that if there was a huge integration between the AOCs and the network manager, then we would reach some more effective solution? Is it what you are trying to demonstrate, or otherwise, or maybe try to find the minimum information needed to exchange between network manager and AOCs? And so I'm trying to recap a little bit what you are trying to research. What is really the topic you want to learn and progress?
That's a really interesting question, because I don't think we've got as far along with that as we might have wanted to. We've gone a long way with the algorithms for the AOC and with the network manager and with developing things like uncertainty handling and different features of those algorithms. We have put them together. We had to do some interesting work in making them work together in terms of how the AOC would interpret things sent back to the network management. I think my feeling is that we've really only just made a start on that, because you're right, there's a lot of complexity in the interpretation, and particularly if you start talking about the realistic scenario where you have multiple AOCs, you've now got a big multi-agent system where you put, I mean, we had to do some work to make sure that they just didn't end up fighting against each other by continually sending back and forth things that, you know, would say it's a multi-agent systems problem, which invokes all problems about what is the information exchange needed and things like that. We've learned a bit about it, that aspect, not as much as we learned about the other aspects that we worked on.
Just another remark. What we wanted to demonstrate is the benefits of taking into account the uncertainties. And the exchange of information is the AOC is computing the trajectory and is given as is computed by the AOC. So the network manager is not recomputing the trajectory. That is the problem that you have now with the network manager, because you have an uncertainty there when you exchange part of the trajectory and then you recompute it in the network manager. This is not considered in the scope of the project, this uncertainty that you have with the trajectories. So we are taking the trajectories as are computed.
Provided by the
yeah, they are provided. It's like the airlines now give you all the trajectory as computed by them, which is not the case now. But
yeah, but on the other hand, they are in reality not really, I mean, airspace users are not really ready to provide full information like in this model.
It's true. But
and the decisions depend on the business model of the airspace users.
But the purpose of the project was to see the benefits of taking into account the uncertainties in the network manager, not the exchange of information between the AOC and the network manager. This would be another issue.
The uncertainty, therefore, would be the decision made by the airspace user rather than the weather itself.
The thing there's another aspect is that we know, so for example, we know that the network manager, it's mathematically feasible to put things in there where the network manager could suggest reroutes. And yet at the moment we are sort of, the way we've drawn the boundaries are that the AOC is responsible for determining the route, so we don't exploit that capability. If you wanted to do that, there might be a system benefit from that, but where do you draw the boundaries about who's responsible for what gets very confused when that comes up. So there's a whole lot of interesting questions wrapped up in that.
And there is a lot of sensitivity.
Okay, thank you very much. I think we conclude here. Thank you.
Thanks.